So in this video, we're going to talk about the Chapter 9 notes, which deal with factoring. Okay, so factoring, in this case, factoring polynomials is what we're going to be doing in this chapter. So think about what a polynomial is, right? It's those expressions with more than one term added or subtracted. So when we're factoring polynomials, we want to break apart the polynomial into two or more expressions that multiply to give us the original polynomial. So this is like factoring with numbers in some senses. If I ask for factors of 12, you might say 3 times 4, because 3 times 4 multiplies to be 12. The difference here is that with a number we have lots of pairs of factors that are sort of equally at the same level in terms of being broken down. And here we're going to have one possible answer for our factored form of our polynomials. So this first page of notes is kind of some background information. It might seem not really relevant at first, but you'll see that as we get into factoring, we'll use these things we're reviewing here. So we're first going to start out thinking about factors of numbers. So we're going to think about how we've listed all of the factors of 24 before. So if we were going to do it in a really orderly way, we'd go in order: 1 and 24, 2 and 12, 3 and 8, 4 and 6, 5 does not go into 24 evenly, and then we'd be back to 6, we'd be repeating. So for 18, 1 and 18, 2 and 9, 3 and 6, if we try 4 and 5, neither one of those goes into 18 evenly, and then we're back at 6. So if we look at these factors, now in C, it asks us to list all of the common factors of 24 and 18, numbers that are factors of 24 and factors of 18. So I'm just going to highlight them here. We have 1 is in both lists, 2 is in both lists, 3 is in both lists, 4 is not, 6 is, 8, 12, 24, none of those are over here, which also means that none of these match up. 8, 9, and 18 don't match up with anything on the 24. So if I'm looking at all of the common factors, we have 1, 2, 3, and 6. We want to know what the greatest common factor is. It's just the biggest factor that they have in common, just like it says. It's going to be 6. Okay, and we'll use this, being able to find the greatest common factor, in just a minute. Let's do another example. So we're going to list all of the factors of 30. So 1 and 30, 2 and 15, 3 and 10, 4 does not go evenly into 30, 5 does, 5 and 6. If I kept going, I'd get 6 times 5, which is repeating those factors. 16, 1 and 16, 2 and 8, 3 does not go in evenly, 4 and 4, obviously I would be repeating if I kept going. So now, greatest common factor. Well, let's think about all of the common factors first. 1, 2, not 3, not 5, not 6, not 10, not 15, not 30. So my only common factors are 1 and 2, so the greatest common factor would be 2. Now let's think for a minute about exponential expressions and how we would find greatest common factors. So let's say we had x squared and x to the 5th. Okay. So just bear with me here when we talk about this for a second. So we can think of x squared as x times x. We can think of x to the 5th as x times x times x times x times x, right? So I want to know, can I take an x out of each of those expressions? Could I say, okay, I'm going to take an x from you, and I'm going to take an x from you? Well, yeah, I can. I just showed that with my highlighting. Can I take an x squared out of each of these? Yep, I can take a second x there and a second x there. That's x squared and x squared. Can we take an x to the 3rd out of each of these expressions? Well, here's where we kind of get tripped up. I can't take x to the 3rd out of this first expression x squared because there aren't 3 x's. I can take one here, but I can't take an x to the third out of the first expression because there aren't enough x's, so no. Same thing with x to the fourth. I can take x to the fourth from the right side, but not from the left expression. And same with x to the fifth. So if I wanted to pull off the same number of x's from each of those expressions, I would have to stop at x squared because I ran out of x's in the first expression. Okay, let's look at another example. And I realize this just seems very abstract for right now. We're going to put it together in a minute. So let's write x to the fourth out in an expanded form. It means x times x times x times x. And x to the seventh. 7 x's multiplied together. So if I want to now look at this question right here, what is the largest number of x's that can be taken out of each expression? Well, I can take an x out, I can take a second x out, I can take a third x out, and I can take a fourth x out. And then I'm done. I kind of run out of things, right? Because I can't take a fifth x out of the top one because I've run out of x's. Same thing with those. I could take x to the seventh from the bottom, but I could only take up through x to the fourth from the top. So this x to the fourth and here x to the second are actually our greatest common factors for these expressions. The greatest common factor of x squared and x to the fifth was x squared. The greatest common factor of x to the fourth and x to the seventh was x to the fourth. So if you look, it ends up being the lowest, or if you want to think about smallest, the greatest common factor ends up being the lowest or smallest exponent on the variable. So in this case, let's say number 4, x has an exponent of 4 and x has an exponent of 7. Well, that tells how many x's there are. So I run out first with that smaller exponent. Okay, now this line right here, this sentence for each of the following, that's supposed to be on the next page. There was just a spacing issue apparently here. So we want to find a pair of numbers that multiplies to and adds to the given number. So again, we're moving on from the greatest common factor, but this will all get put together in just a few minutes. All right, so for my example, I want to find a pair of numbers that multiplies to 8 and adds to 6. Okay, so I can find a bunch of different numbers that multiply to 8. And I can find a bunch of different pairs of numbers that add to 6. But I want the set that does both at once. So let me just show you, you have the answer right here, but let me just show you how we would do this. We're going to start out by thinking about numbers that multiply to 8. Okay, there are fewer of those. Those are the factors. So if I think about numbers that multiply to 8, I have to find the factors. So 8 would be 1 and 4. Oops, sorry, 1 and 8. Okay, let's try that again. 1 and 8, 2 and 4. Okay, those are both numbers that multiply to 8, pairs of numbers. Well, now I want to find out which of these also adds to 6. Okay. Well, 1 plus 8 would add up to 9. 2 plus 4 would add up to 6. So 2 and 4 is a pair of numbers that does both of these. It multiplies to 8 and it adds to 6. So my numbers are 2 and 4. You can see here it can be in either order. And this will be part of a larger procedure in our factoring in a few minutes. Okay, I want to find a pair of numbers that multiplies to 12 and adds to 7. So 12, let's start out with the multiplying to 12. So we're going to multiply to 12. 1 and 12, 2 and 6, 3 and 4. Okay, I want the one that adds up to 7, so I check each of those pairs. This is the one that would add up to 7, 3 and 4. Okay, Next, we're going to find a pair of numbers that multiplies to 30, adds to 11. So again, we will start out by thinking about factors of 30. So 1 and 30, 2 and 15, 3 and 10, 5 and 6. We want one that adds to 11. So this is going to be my pair that adds to 11. All of those pairs, if I chose 1 and 30, it would make the first part true, it would multiply to 30, but that would add to 31 instead of 11. Right? So we have to make sure we're doing both. So 5 and 6, again in either order. Next we have one that also multiplies to 30, but this time we want to add it to 13. Well, we can see if we look over in our same list, here's the pair of numbers that adds to 13. So we get 3 and 10. Okay, so we're finding a pair of numbers that makes both of those things true. Okay, now number 8 and 9 and 10 start introducing something a little extra. If you look at these, you see that we have negatives now. So I want to find a pair of numbers that multiplies to negative 15 and adds up to 2. So I'm still going to start with, the multiplying part. So I want to start out by giving factors of that number. So I'm going to just start with positive. And I'm going to forget about the negative for just a minute. And I'm just going to find factors of 15. So 1 and 15, 2 doesn't go into it, 3 and 5, those are all my factors because 4 does not go into it. All right, now I know that I need two numbers that multiply to negative 15. What that means is that those two numbers are going to have different signs. That's how I get a negative answer when I multiply. And if I look over here, I'm going to see that those two numbers are going to add up to 2. So I already know that I have different signs. If I'm adding two numbers with different signs, my answer is whatever there are more of. So in this case, there must be more positives. Okay? So we know that when we add a positive number, whatever it is, and a negative number, right, they cancel out, and then whatever I'm left with is my answer. So in this case, if they're adding up to 2, that must mean I have more positives than negatives. All right, so right now my numbers here multiply to positive 15. I want them to multiply to negative 15. So I'm going to give them different signs. I'm going to make one number in each of those pairs be a negative. Well, I want more positives, so I'm going to make the smaller number in each pair a negative. What do these add to? Let's see, so negative 1 times 15 does multiply to negative 15. These add to positive 14. Negative 1 plus 15 is 14. The second one adds to positive 2. So this is my pair that I need then, negative 3 and 5. You can switch the order, but your negative still has to go with the 3. Go ahead and try the next one. So you need a pair of numbers that multiplies to 15, but this time it adds to negative 2. So think about what that does differently. And my hint to you is going to be not to use the pairs of numbers that you have up above. Okay, not those specific ones. So go ahead and pause the video and see what you can do with this one. Okay, so hopefully you started out again by thinking of factors of 15. Then again, we want it to be negative. That again tells us we're going to have different signs. However, this time it adds to a negative, so that means my two numbers with different signs added up to a negative. That means there were more negatives. So now in each of these pairs, I'm going to make the larger number the negative number, the larger absolute value. So now if I add these two, there are more negatives, so I'm going to add this to negative 14, and I'm going to add this to negative 2. So now I have 3 and negative 15. They both multiply to negative 15, and they have similar answers when we add, but one is positive and one is negative because of what there are more of. Okay, number 10. Find a pair of numbers that multiplies to 10 and adds to -7. So let's think about 10 first. 1 and 10, 2 and 5. Okay, now, if they multiply to 10, that tells me that they have the same signs. Okay. When it adds to 7, to -7, this tells me they have the same signs. I could have two positives or two negatives. Well, if I had two positive numbers, if I add two positive numbers, I will never get a negative. So this tells me that they must both be negative. So here in my factors, in this case, both are negative. Well, this first one, this first pair adds to -11, and the next two numbers add to -7, and those are the ones I want. -2 and -5. Okay, so you have to think about those signs. And again, this seems kind of out in left field at the moment, I realize, but we're going to be using this in just a minute. So now let's move on to our actual factoring. And as we said here, factoring is breaking up polynomials into expressions that multiply together to give us what we started with. So we're going to have a whole bunch of different types of factoring. I think we'll have 5 altogether by the end. And the different kind of factoring you do is determined by what type of polynomial you have, okay? But we'll talk about that, and I sort of have like an overview at the end, and it'll be fine. Okay, so let's just take it one thing at a time. So right now, you're going to learn about factoring out a greatest common factor. So for these few questions here, that's the only thing you're going to know, so we can just work on greatest common factor. So remember back to that first page. We talked about a greatest common factor for numbers, right, is the biggest factor they have in common. And then we talked also about a greatest common factor for variables. And so we want to put those things together here to find the GCF, find the greatest common factor. So let's look at this first one. I have 5x cubed plus 20x. So I want to first find my greatest common factor, and it's going to have two parts. It's going to have the number part, and it's going to have the x part. So let's just look at the numbers, 5 and 20. If you need to, write out your factors for each of those, and then we can look for common factors. So if I'm looking at common factors, I see that 1 is in both lists and 5 is in both lists. I want the greatest one. So my greatest common factor, the number part, is going to be 5. Now notice that, 20 isn't in both of these lists because 5 can't have a factor of 20. That wouldn't make any sense. Not an integer factor. So your GCF has to be the biggest it can be. Think about this for a second carefully when I say this. The largest your GCF can be is as big as the smaller number, right? I can't have a GCF of 20 because 20 can't go into the smaller number of 5. So my GCF could be 5 because 5 goes into 20. Or it could be smaller than 5. Now I need to figure out the x part of my GCF. So you don't have to write it out like this every time, but let's just see what's happening here. So if I have this, x cubed is x times x times x. X to the first is just x. I can take 1 out of each of these. I can't take any more out because I run out in this x to the first power. So my GCF, my greatest common factor I can take out, is just a single x. Again, it ends up being, this is x cubed and this is x, your greatest common factor, the exponent part, ends up being the smallest exponent that you have. So my greatest common factor is a 5x. Now this right here that I'm writing is sort of like a preliminary step. Because remember that factoring means I'm breaking it up that polynomial, into expressions that multiply together to give us what we started with. So if I just said, oh, my answer is 5x, well, 5x is not the same thing as 5x cubed plus 20x. It's part of it. So for my actual answer, I'm going to write that GCF, and then in one set of parentheses, I'm going to write what's left from each of those terms. Okay, so in other words, one way to think about it is if I had 5x cubed, that first term, and I took out, or in essence divided out 5x, what would I have left? Well, 5 divided by 5 is going to cancel, and 3 minus 1, right, quotient rule, is going to be x squared. So all I have left here is x squared. Stick with me for just a second, and then we'll kind of look at it a different way also. Plus 20x divided by 5x is going to be just plain 4. Okay, now I'm going to tell you that this is your answer, and it might not look any simpler than what we had before, but when we move on to chapter 10 and we're solving equations like this, similar to this, we need to have them in factored form so that we can solve them. Okay, you'll see in next chapter why that is, how that works. So how can I check this? And this check is also kind of another way to think about it as we're doing the problem. So here's my check. I take what I have here, 5x times x squared plus 4, sorry. And remember that when I'm factoring, I want my answer to be 2 or more expressions that multiply together to give me what I started with. So 5x times x squared would give me 5x cubed. That's using our stuff from chapter 7 and 8. 5x times 4 is positive 20x. Is that what I started out with? Yes. So that checks. Okay. And that's another way you can think of this as you're factoring. So sometimes I like to think, let me just write over here, if I had my GCF, I like to think, okay, 5x times what would give me 5x cubed? Well, I don't need anything for the 5, but I need the x squared. And then I might think, okay, 5x times what gives me 20x? Would be 4. Okay, so, you know, I kind of think about it that way sometimes too, like a backwards multiplication problem, rather than explicitly thinking of it as division. Okay, let's try number, let's see, what do I want to do? Let's try number 4. All right, so this one looks like a big old mess, but we're just going to take it one step at a time. So if I look at a greatest common factor for 25, 30, and negative 15, I'm just going to tell you now that the greatest common factor for that would also be 5. Now I'm going to look at the x's and the y's. So my x's, I have x cubed, x squared, and x. So you can think about what the expansion would be, or you can just look at those exponents. If I wanted to take some of these out of there, I could take one x out of each of these, and then I'd be stuck because I'm out of x's in that last term. So I can only have x or x to the first. And then if I think about my y's, okay, now if I look and see what I can do, I can take out a y from each of those. I can take out a second y from each of those. I can take out a third y from each of those, and then I'm done. Again, notice that's the smallest exponent. So 5xy to the third is going to be my GCF. So now I have that 5xy to the third. I have my parentheses, and for each of these terms, I'm going to think about what is left when I divide out that GCF. So I can either think 5 times what is going to give me 25, which would be 5. X times what gives me x cubed, well, that would be x squared. Y cubed times what gives me y to the fourth, just a plain y. Or I can think about it this way too. I can say 25 x cubed y to the fourth over 5xy cubed. 25 divided by 5 is 5. Quotient rule. Okay, either way, gets you the same answer. Next part here is plus 30 divided by 5 is 6. X squared divided by x is x. Y to the fifth divided by y to the third is y to the second. And then finally, negative 15 divided by 5 is minus 3. X divided by x cancels out. Y cubed divided by y cubed cancels out as well. So here is my answer. Okay, again, you can check it by multiplying it back. And yes, it looks kind of messier almost than before, but again, we need it in this factored form to move on with some things we want to do with it. All right, let's look at number 5. The other ones you can try on your own. So if I look at these two terms right here, I have 15 and 3. The greatest number, the largest number they have in common is 3. If I look at the exponents, the largest value they have in common is just x to the first, and the largest for the y is just y to the first. So if you're not sure where I got that from, pause the video, take a step back, look at how I would have, what I would have thought about if I had written out those x's and y's. So now I have 3xy out here. So I can write this out, or you can do it in your head. If I have 15x to the third y squared over 3xy, 15 divided by 3 is 5. Use the quotient rule here. 3 minus 1 is 2. Y, 2 over 1 is just y. So that's what I have here. Now, when I look at this next term, the next term over the GCF looks kind of funny because that last term itself is the GCF. Okay, what I can't do, so I'm going to write it for a minute and then I'm going to erase it. I cannot just say, oh, that cancels out, so it's gone. Okay, think about why. If I were to check this by multiplying, and I multiplied 3xy times 5x squared y, I'd get 15x cubed y squared, and that would be it. I would never get this second term. So that can't be quite what we do. Instead, every single term in my original polynomial gets a spot in my answer. So 3xy divided by 3xy, anything divided by itself is just 1. So I have plus 1. Now if I were to check it, multiply these two, I get my 5x cubed y squared. I multiply these two, I get plus that 3xy. Okay, so that's finding GCF. Now, we're going to put it aside for a minute while we start this next section, but then you'll see that looking for a GCF is actually the first step of every single factoring problem. Sometimes there won't be one, and you move on to the next method, which you'll know by then. Sometimes we find a GCF, and then that's all we can do, and we're done, like the ones here. And sometimes we'll find a GCF, we'll go through this process, and whatever I have in my parentheses, like this for example, then can get factored again. Okay, so that we'll see all those different scenarios. All right, so we're going to next just set aside the GCF for a minute, and we're going to look at one situation of a type of polynomial that we might factor. So we call these easier trinomials, okay? So trinomial, and we know tri means 3. So these are polynomials that are in this form, ax squared plus bx plus c, where a, b, and c are numbers and a equals 1. So what does that mean? Well, if I look at this, a, b, and c are numbers. So it might be, for example, something like 5, oops, wait, let me go back for a second. So a, b, and c are numbers, and in this case, a equals 1. So there's going to be a 1 there in front of the x squared. So I can write it, I don't have to. X squared plus 3x minus 5, right? A is 1, b is 3, c is negative 5. You can see I called these easier trinomials. Harder trinomials are when a is not 1. So it's something like 5x squared plus 3x minus 5. Okay, we'll worry about those a little later. Before we get into this, let's first review our multiplying. So let's just forget about factoring for a minute. Take each of these problems and multiply it and see what you get. So x times x is going to give me x squared. X times 4 is plus 4x. Then plus 3x. And then plus 12. Okay, and then I see that I can combine those like terms in the middle. So I get x squared plus 7x plus 12. Okay, so pause the video And please go through and multiply the other pairs here. And in each case, write out that middle section with the two middle terms, okay? And then go ahead and add them, just so we can we're looking for some patterns here. So go ahead and pause the video and do that, and then we'll go over those. Okay, so hopefully you paused the video like I did and did these. So let's take a look. We're going to look for some patterns in here. So if we look at, we're looking at this last version of it in each case. If we look at the first term in each of these, it's x squared. Well, that's easy to see why. It's because we have x times x always gives us x squared. Okay, easy enough. Then let's look at the last term. So the last term in the trinomial is either positive 12 or negative 12. Oops, this one here should be positive, sorry. So positive 12s or negative 12 is what our answers were. Let's think about where that came from. Well, in each case, that came from that last part when we multiplied 3 times 4, or 3 times negative 4, or negative 3 times 4, or negative 3 times negative 3. Sorry, negative 3 times negative 4. So notice what happened. When the signs are the same, like in the first one and the last one, we get a positive 12. When the signs are different, like in the middle two, we get a negative 12. Okay, so the last term comes from multiplying the last term of each binomial, right? So the binomials are what are in these parentheses because they have two terms. I multiplied the last term, and that's where I got this last term. So this one is this, right? That's where this came from. Okay, next let's look at the middle term. So this middle term, I have a bunch of different things that happened here, and I can just for continuity's sake put in a 1 here. You don't need it, right, for either negative or positive, but okay, so for the middle term, I got 4 different answers. I got 7, I got negative 1, I got positive 1, I got negative 7. So where did that, like, let's look at the first one. Where did that 7 come from? Well, that 7 came from adding these two right here. And where did the 4x and the 3x come from? Well, when this 4 was multiplied by the x and when this 3 was multiplied by the x. So negative 4 and 3, they added to be negative 1. They are coming from here, negative 4 and 3. Make that bigger so you can see it's blue and yellow. Makes green. Okay, in this third one, positive 4 and negative 3 gives us 1. Here's my negative 3, here's my positive 4. And finally, negative 4 and negative 3, here they are, they add up to negative 7. So where did that middle term come from? Well, the middle term came from adding two products, and the coefficients are the last term of each binomial. Okay, so what's that mean? The middle term, the one in blue, came from adding two things. They added products. 4x and 3x are products because I got them by multiplying. 4 times x gave me 4x, 3 times x gave me 3x. Where did those numbers come from? The 4 and the 3 and the negative 4 and the 3 and the 4 and the negative 3? Well, those are also those last terms in each of those binomials. So look at what we have here. Those last two terms in the binomials, the 3 and the 4 and the negative 3 and the positive 4 and the negative 4 and the positive 3 and all that, I multiply them to get the last term, and I add them to get my middle term. Think back to what we did at the beginning, right? I need two numbers that multiply to blah, 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 and add to blah, blah, blah. Two numbers that multiply to 12 and add to 7. Two numbers that multiply to negative 5 and add up to 4, right? Whatever it is. Okay, so when we are factoring, we are starting, oh my goodness, that was a really bad line. Start over. When we are factoring, we are starting here and working our way back to having it in factored form like these over here. Okay, so that's why we need to do this. We are given this trinomial and we have to act like a detective to figure out what the binomials, what those factors are. Okay, so let's go ahead and try a little bit of this. So in this first example, we need two numbers that multiply to something and add to something. And really this thing that I have right here is what we're thinking every single problem. Okay, we don't always write it out quite like that, or on the paper it won't be, but I'll show you. I always kind of write it out in shorthand. So remember, I multiply to this last number, I add to the middle number. So I need two numbers that multiply to 2 and add up to -3. Now, you might be able to do this one in your head, but let's go through the process. 2, the only factors of 2 are 1 and 2. This tells me that the signs are the same because it multiplies to a positive, but then if they add to a negative, that means there are more negatives. Oops, that's not what I mean at all. They have the same sign, so that means they are both negative, right? So same signs, just from the 2, that could mean either 2 positives or 2 negatives. Well, 2 positives would never add to a -3. So they must both be negative. So now we make both of them negative. Does that work? Yeah, -1 times -2 gives me 2. -1 plus -2 gives me -3. So I can put those right into my binomials. Now we know with all of these, it's just going to be x times x. That's how I get that 1x squared. And then I just put these numbers in here, -1 and -2. The order doesn't matter as long as you have the sign right. Okay. How do I check it? Well, I check it by multiplying. So I would take x minus 1 and x minus 2. I would get x squared minus 3x plus 2. The 3x came from these two, minus 2x and minus 1x. And that's my answer. Okay. What I would like you to do is I would like you to pause the video and try, let's see if I can get this into here. Okay, so try 2, 3, 4, 5. Actually, you don't have to pause the video. I'm going to end the video here. Try 2, 3, 4, and 5. When we get back, we'll go over those. And then some of the other ones, let's see, 6, 7, and 8 are a little bit more complicated. So I want to kind of go over those together. So let me stop this here. So you can just pause the video so you can write those down if you don't have the notes in front of you. And then in the next video, we'll start by going over those. All right, thanks.